specialist group, which is one of their usual once a month additional to the schedule, because Nik had to be moving somewhere by his new destinations, and he kindly agreed to present the talk which suited us to our schedules and his schedules. So Nik will present a talk on high-level development and debugging of FPGA-based network programs, which involves pretty big collaboration, as you see, number of people who are shown named there, and a big project with very big promising future.
Thank you. And it's truly a pleasure to come talk to you guys outside of university. Usually, I usually present at very different organizations, speaking to very different people. And in the course of this, I'd be interested to know if you have used anything similar or you have any need for anything similar. And do feel free to stop me during the talk to ask questions. There's no need to wait till the very end, just interrupt me. So some of you might already have some understanding of how FPGAs work and how they're programmed. I thought I'd start with talking about that to introduce the topic, and then kind of gradually talk about what we're trying to do to improve on that. So, if you were to look at the die photo of a recent microprocessor, you'll find that it's organized into at a higher level in functionally few but very sophisticated, very complex parts. And these, as one might expect, work together to achieve some coordinated service. Now, if instead were to look at FPGAs, a very different picture will emerge. So we have much less sophisticated components, subparts, but many more of them. So we have, as you can tell on the right over there, we have a grid of CLBs, configurable logic blocks. And these you can think about as a generalization of a logic gate. They're a logic gate that you can specify whether you want it to be an AND, or it can also be a couple of gates. It also has memory, so that's how there's memory there. So those are the orange blocks on the right. There's also memory blocks, so you also have onboard memory, as you do in a CPU, right? You have cache, you have registers, you have different types of memory that is available here, and connecting everything together, you have what's called labeled there the interconnect. So you have a fabric that allows you to kind of wire together the configurable logic blocks and the memory to generate the circuit that you've designed, right? So this is, you can look at an FPGA as a substrate that is kind of a configurable circuit plus memory, right? So you can have combinational and as well as sequential logic encoded there. And there's obviously in practice there's much more to it, and there's much more detail, but the 30,000 foot view is that it kind of, you have these components that aren't super complex as a CPU core would be complex, for example. But you have this flexibility to configure and connect them. And programming an FPGA at the lowest level consists of writing into SRAM, right? So there's memory that, when written to, it configures memory to RAM to be ROM, or the generalized logic gates to be specific logic gates, and wires everything up together. Okay, so that's kind of at a high level what an FPGA looks like, and what it provides for you to program. And the timeliness of this research is that, well, FPGAs are becoming more powerful. So the photo I showed you there of one of the earliest commercial FPGA had relatively few logic blocks. But over the years, the number of logic blocks has increased dramatically. So FPGAs can encode much more complex programs. And they are being picked up in other industries. So FPGAs have been used for vision processing, for radar, for high frequency trading. They're also making a presence in data centers. So some companies use it to accelerate their research. Other companies are now making it available for their customers to use as a resource that you can rent. Now, despite the appeal of using FPGAs, having this reconfigurable circuit that could consume much less power than a CPU would, they are difficult to program and debug. This is the Achilles heel of FPGAs. This is what has been, what is the gripe that many people have about FPGAs. It's not that they're difficult for novices, but they're also difficult for experienced people, and not always for technical reasons. A technical reason why it can be hard to program FPGA is because part of the process involves solving an optimization problem to place and route your circuit, and that just takes time, right? So it can take hours, days to get the final stream of bits that configures the SRAM I mentioned. But other problems are non-technical. It's just the way the market is, and the incumbents tend to be very closed about their devices and their stack. So you have to go through their tools, and these tools are not open. So they have not been improved by innovation to the extent that open source software development tools have been. Right? So this is a bit of a problem. Now, in order to try to alleviate this, there's been over 3 decades worth of research that's been directed at improving the programmability of hardware, and over 2 decades of commercial tooling for this. And the experience has been mixed, because often, as you appreciate, to gain something you must give something else up, right? So in order to describe hardware using a higher level language, you are using a language that has not been designed to program that hardware. So you might lose control over the finer details and the timing of how that hardware is working. So far I've talked about the FPGA-based part and the high-level development, the desire for having a higher-level development for FPGAs. So let me talk a bit more about how FPGAs are programmed, different ways of programming FPGAs, and focusing on networking. Though a lot of this is also transferable to other areas. So at the lowest level, you could specify, if you had the patience, the gates and interconnections, right? But nobody works at that level. So a much more common entry point is using a so-called hardware description language. The principal ones are Verilog and VHDL, and this provides you with a very, I think, controllable interface to the hardware that you get. Another approach is called high-level synthesis. So the departure point here is taking a language like C and translating that into an HDL, and then using the vendor's tool chain to generate the so-called bit stream that programs the FPGA. Alternatively, one might start from a domain-specific language. So I've mentioned some languages there that are intended for network programming, and then use a compiler for this language that will generate HDL, but could also generate a general purpose description in some language that can be translated into an HDL. So I'll talk a bit about the different languages being used here, starting with hardware description languages. So using such a language offers you a lot of flexibility, and these languages were not always designed to be able to generate hardware. Some of them were designed kind of to be able to simulate above generating, but over time they've been changed so that the kind of code you write is very likely to be synthesizable into hardware. The difficulty in using these languages, however, is that a chasm opens up between what you're thinking and what you're writing and how that is interpreted. And this is fairly familiar from software programming, right? We have to keep in mind sometimes the architecture that we're writing for, and keep in mind how the compiler might be translating that in order to achieve what we want to achieve without a nasty surprise having to debug that. So, for example, in these languages, we might specify reg for a register, but we might not get a register. It might be turned into something else by the compiler. There is ample scope for inference and mapping to the underlying substrate of the FPGA. And this is convenient. This is great because it's an abstraction, but it doesn't jive very well with the high level of control that we thought we had when we were writing this language. So, as ever with language designs and language choices, we have to suffer some pain, right, to be able to get our ideas into some functional form. So I came across an example recently, which is an anecdote of what one might have to do to use these languages. So here I have a snippet in C showing a struct, and I'm using the bit fields notation on the right to specify how wide each field is in bits. So that's the first declaration there. And then I have a second declaration where I am declaring an array of such nodes. Okay. Now in the project I'm on, we use a specific version of Verilog 2001, and it does not support the syntax. It supports a much more expanded form, which feels rather primitive when looked at with the eyes of a 2017 software developer. Unless you are working in very, very niche, low-power devices with very poor compiler support, you wouldn't expect to code in a very expanded way. But for people who have been programming in that style before, they get used to it and just carry on. Okay, so turning to DSLs, domain-specific languages. So, in contrast with hardware description languages, you have much less flexibility, right? You can't do everything in a DSL because, by design, the language should not allow you to do everything, right? It should only allow you to do what happens to fall in that domain. Moreover, it's not even that, because the domain is a fairly amorphous thing, right? It's whatever the designers of the language thought might fall in that domain. And as long as what you write falls in that conception, you should be good. The tools will help you translate what you wrote into a form that is very likely to be efficient. If you don't, if it doesn't, then you're kind of on your own. And such languages often provide kind of providing external support and breaking out into a hardware description language to describe the feature of the system that happens to fall outside the domain. However, in this talk, I'll be focusing more on high-level synthesis. So high-level synthesis, I think, provide us with a very sweet spot to address, because we are not giving up on expressiveness. We are retaining control, but we're also retaining some of the intuitions and the linguistic knowledge that we have from mainstream languages. So I'll tell you a bit more about HLS and what it boils down to. So it involves using a familiar language. Now, I know that talking about languages and best languages can be very religious, so I have quoted it there just for protection. But also when we are using a language such as C, or in our case we use C# to program hardware, we're not using the language in its natural habitat, as it were, right? So C was never designed with FPGAs in mind, neither was C#. So that's what I mean by quoting familiar, because we cannot make the usual assumptions about how the language is working. And that comes to play later when I talk about debugging. And usually in HLS we're not using the full language. We're usually using a subset of the language, and often that's not a bad thing, right? Because expressive languages can give programmers plenty of rope to hang themselves with. So having a more constrained, focused subpart of the language is often not a bad thing. And it might still require, for tuning, however, rather than expressiveness, breaking out into hardware description language to make use of existing features. So HLS in a nutshell. So is the clock signal visible from the back? So we have a clock signal there. So the goal of HLS is to get some high-level language, C# in our case, and schedule it in time. That's what it comes down to. It's a pretty difficult problem, but intuitively it involves creating in our case, a finite state machine from the C# description of the system. So what is to give you an intuition what it would look like. Say we have a program where we have two subsequent statements, A and B, and A consists of evaluating some expression and assigning it to X. And B consists of evaluating some different expression, possibly, and evaluating it to Y, and assume that X and Y are not A-list, so they don't interfere with one another. So one way of scheduling these statements, since they don't interfere with one another, is, well, they could happen simultaneously, right? So they're both scheduled to occur in the same time step. So the sequential way of thinking that we have when reading C, for example, no longer holds over C#, right? The HLS compiler might move things around. So say we have another kind of a modified program where between lines A and B, we have a line C, which involves calling function f and passing it the value of x. And let's assume that f is side affecting. It affects the expression that y is going to receive the value of later, right? So we can't schedule these to occur within the same time step because we have to know the value of one before computing the value of the other, right? So a happy solution to this would be to separate them out in time. Now, depending on the frequency at which the chip is running, it might be that we can't do everything, that we can't do a full computation within a single time step because the frequency might be too high and the computation is too complex, so something has got to give. So in this case, line B involves a more complex expression that cannot be computed within the time of a single clock. So what the HLS compiler then has to figure out is how to break up the expression in order to complete part of it in one time step and part of it in the other time step. If it happens that this can be parallelized, maybe they can both be completed in the same time step. And if there's no necessity for A to be completed before B, it might well be that B is evaluated before A, right? So the point of this is going back to the kind of the quotes around familiar, that the HLS compiler is at liberty to move things around as it gets the job done. So that's what HLS ultimately comes down to, right? Trying to schedule operations in time. And if you look at marketing material from HLS compiler vendors, you notice that they talk about aggressively packing operations into each clock period. So that's to give you an intuition of what HLS is, because I'd like to now kind of elaborate on the title of the talk and specify that it's going to be about using high-level development debugging of network programs on FPGAs using HLS. Now, why is this a bad idea? Well, one objection is that performance will suck. Remember I told you about this chasm between what you think you're writing and what you are getting, and the HLS compiler at that stage might not know what clock frequency the FPGA is going to run at. So it can produce a scheduling that down the line, during the later phase, is not going to work. So then you have to go back and assign a different schedule in time. So we get around this problem by breaking out two modules written in HDL, in the hardware description language. So this allows us to get the best of both worlds. So at worst, we are gluing together HDL blobs. At best, we're describing complex logic in a language that is less amenable to misinterpretation. Because it's a language that we know better, or it's a language that one could argue is qualitatively simpler than something like Verilog, for example, with different sorts of assignment and different kind of more parallel semantics to keep in mind. Another objection is, well, such tools are expensive and closed source, but there's also academic options. That's something that we use. I'll tell you a bit more about it in a bit. Another objection is that these high-level languages that we're departing from, they were not designed with hardware programming in mind, right? So inevitably you're gonna come across features that you'd like to express, but you can't. The language was not designed to carry that, and there are ways to work around this. So that's what we do. I'll tell you a bit more about it in a bit. And finally, the HLS compiler can take you from, in our case, C# to Verilog, but and then you can use the vendor's toolchain to take you from Verilog to actually running something on FPGA. But what about running it on the CPU? You might need more support, right? The compiler is great, but it's only part of the story. You need the runtime environment and runtime library, and we provide that to facilitate running these networking programs on the CPU for testing and debugging. So I'll tell you a bit more about that too. So to kind of recap the objectives, we'd like this to be useful for hardware engineers, primarily to help them get their work done quicker and better and prototype things more easily. It's also great if it can be useful to non-hardware engineers, and there is scope for that. So somebody who understands C# is going to be able to understand the code that I'm going to show you in this talk. But we don't want to compromise on performance or on utilization of resources, right? So that's our goal. So the system we devised is called EMO, and it works by taking a software description in C# of a network program and ultimately giving you a hardware description of a network program. But no, it doesn't stop there. It also supports running both the software description and the hardware description. So the first component of EMO is HLS. So for this we use the HLS compiler called Kiwi, which takes .NET bytecode and generates Verilog. And Kiwi is the fruits of research project at the University of Cambridge and at Microsoft Research, where the primary authors are David Grieve and Satnam Singh. And you can find more information at that URL. So this is what enables us to take code that looks like this, and this is C# goes through any C# compiler and generate Verilog from that. Now, when looking at this code, you're going to see definitions that are not inherently C#, right? For example, there is hashcam there, or there's a naughty queue. That's part of the library that we have that you can use from C# and that is backed by hardware modules. So, and that's the next part of the picture here. It's not only the compiler, but also having library support, so that you don't have to write everything from scratch. So then the third part is the host environment. So, as I mentioned, a compiler is a very useful thing, but ultimately it's just a translator. You also need an environment that allows you to execute the code that you wrote, and PAX, the URLs there, is a system that provides you with a very simple abstraction for writing network code. It's kind of the obvious usual abstraction, which is a blob of logic with ports. And you configure these ports to receive information or send information. So in truth, you wire them up with network cards on your system, be they real or virtual network cards. And data is going to be ferried between these virtual or real NICs to the logic, processed by your logic, and then ferried back through the same ports, through different ports. And code, and this is all C#, right? So code looks pretty uncontroversial. So this is an example of a network address translation device. This is the code that goes from the outside of the network to the inside of the network. So you would want to make sure that you already have an entry that you recognize that someone from the inside of the network must have spoken to the server at the other end, and that a connection has been established, and therefore I can accept traffic coming from that server, from the outside of the network, back to the inside of the network. And the last piece of the puzzle is the hardware environment. So this is on the other end, where we run the generated Verilog on an FPGA, and we use a net FPGA card. There's the URL over there, and we don't only use the card, but we also use a so-called kind of a reference pipeline that's provided as part of the project that populates most of this graph. So we only need to drop in the main logical core. So that is what we generate from our C# code. And the rest of the infrastructure is used from this pipeline. So I'd say that one of the key things in this, to glue everything together, is the library support that allows us to leverage the two runtime environments and the compiler that binds them together. And we do something called lifting and shadowing, right? So we get Verilog code and we lift it and wrap it as C# classes that you can use from C# as if it was some other .NET class. And shadowing, where we project features of C# or .NET to counterparts on the other side. So let me show you some more code. Let me zoom in on the code. So here we have declarations of variables, but as you'll notice, you also have annotations that specify that these variables are to be related to particular ports, and these ports have names, but they may also have specific widths. And this echoes a remark I made earlier about languages not having been designed for hardware. In a language like C#, you can't easily specify that you need a 5-bit integer, for example, right? Because, well, it's not kind of the usual use case for people programming C#. But in hardware, that might exactly be what you need. So why use 16 or 32? So this is a very standard device used in the Kiwi compiler to allow you to annotate variable declarations and turn them into ports, into hardware ports, so that when you get Verilog at the end, you will have your module will have an interface that consists of those signals and would have those widths and bits. Turning to some code, so you might have seen in the code I showed you earlier a mention of naughty queue. So there might be a better name for such a queue. This this is a queue where you can point to arbitrary elements and send them to the back of the queue as if they had been naughty in constant time. So here we have the C# facing part of the naughty queue, right? So here we are adding an element to this queue. This is the data in, and we're getting back an index, so it's like an array list. So we're getting back the index in memory where it was actually placed. And as you can see here, while externally the external interface consists of a method that's callable by somebody else in the C.NET world, internally we are sending signals across wires and listening on these wires, right? So we are following a certain protocol where we're waiting for a particular signal to go low, and until it does, we're doing nothing. When it does, then it means that us, the customers of this naughty queue, can execute the demand, the request to have an item, an element added to the queue. So we set the command there, we specify the data in, and we set a flag enable to say, okay, I've done my request. We wait for the request to succeed, so we wait for the ready flag to be set, and then we read the data out, and that's what completes the protocol. So I'll also quickly show you what it looks like on the wires. So this is just to reinforce that we are using this in a .NET world, but what we're getting is very much electronic. It has more of an electronic character to it. Circuitry. That's a better word. Okay, so we start off with asserting a reset signal to put the system in a known state, and I'm not sure if your eyes are good enough to discern that the command signal is being set to 1. That means enlist. So we have 3 elements happening there. We have three things happening there. So we have we're asserting a command that says put this item on the list. We are providing the data, and we are also setting the enable signal, right? So we're saying, okay, execute this command for me, please. We notice a few instances later, the ready flag goes up, which is the indication that the memory has done our bidding, and then we can, in this case, I execute another piece of code that tries to read from the list, and we get the expected behavior, right? So we're kind of running the protocol that the memory has been programmed to play, but we're calling it from C# without any knowledge of what's happening on the wires and the variable side. And this is, from an abstraction point of view, this is very appealing. Okay, so now what I've described so far has been pretty generic and has not covered networking specifically. So let me turn a bit more towards that. So I want to introduce 3 kind of levels of thinking. The first, seen in that circle in the middle there, is the packet processing logic. This is the core logic that you described, right? This is what you want to be done. The other 2 layers are infrastructure supporting your logic. So the first layer consists of the pill-shaped gray region there, containing the input arbitrary and the output queues. We call that the data plane, and that is what feeds your logic and what gets the results back. And it feeds it and gets the results back to the rest of the infrastructure, right? So ultimately to the interface with the physical medium. So the workflow one usually follows in our group consists of writing the packet processor in Verilog. So this is, if you remember from a few slides back, this is the logical core that goes in the middle. And then simulating this on a workstation, simulating the data plane on the workstation, rather than simulating the whole thing. A data plane is finding a smaller simulatable unit is desirable because the tests can happen quicker. And for completeness, then testing the whole thing in hardware. So flashing it onto an FPGA and sending packets over the network and looking to see if your code is behaving as expected. So now with by using the Kiwi high-level synthesis system, we get a different branch, right? So in addition to the branch you see on the left there, which was the branch I just showed you, we can also run the code on the workstation as a process now. So we're not simulating it. This is actually a process that can be connected to actual real or virtual network cards. And that is much easier to test and interact with in that format. And moreover, you can also use a network simulator, right? So you can, within your workstation, have virtual hosts wired up together and have them try to communicate with an instance of your logic running in one of these virtual hosts, communicating through virtual network cards. Now, something I should point out here is the timescales. In order to generate a bit stream, for a lot of the logic we have, takes about an hour. Compiling the code to generate the .NET bytecode takes a few seconds. So after a few seconds, having compiled it, you can run it, you can start to test it. It is a much more appealing timescale than the more narrow simulation tests we run, or the more thorough but temporally more costly in hardware tests that we run. Right? So this is kind of what you win by taking the branch on the right. So we tried this out by building several examples of code. So one of them is a learning switch, and the kind of bigger developments were the DNS server and a memcached server. So for those of you not familiar with memcached, it's an in-memory key value store. It's like a form of NoSQL database, and also a network address translation element. So we went about measuring these artifacts against existing counterparts. So we started with the switch, with learning switch, and we measured how it performs against another similarly capable switch, but written in Verilog, right? So we have our switch written in C#, there's another switch written in Verilog, and we want to find out how do they perform relative to one another. And this is telling us how much does it cost us to use this HLS approach, right? So we are writing this stuff in C#, but does it mean that we are getting abysmal behavior? And it turns out that, so if you look at the second part of the table, that is where the performance figures are measured in terms of bandwidth and in terms of latency, and they're comparable. Both, they're very, very close to one another. So that's great. For this simple element at least, writing it in Verilog or writing it in C# is not going to make a difference. For utilization, so in terms of, if you remember the very first second slide, in terms of the utilization of the elements on an FPGA, be the logic elements, so these lookup tables, and memory utilization, is the compiler we're using more and more profligate compared to handcrafted Verilog code. And it is slightly more demanding, but not overly so. So if you look at the figures, numbers, it's very close. So we did this comparison between the C# code and the Verilog code, but we didn't have the resources to write everything in Verilog. So another test we did consisted of pitting our DNS server against a DNS server running in Linux. So I want to draw your attention here to the black and the red lines, because those are measurements made with much more precise hardware. The red line is NDS, which is a DNS server available on Linux, which we run on Linux. And what this graph is showing you is the cumulative distribution function, right? So how, so if we were to weight, so what percentage of the tests have a round trip time under a certain time period, and you can do this by looking up to here, for example, and you'll see that the round trip time there is steadily bigger than the black line, which is I suppose you can discern it's to the very left, and it's also much more inclined than the black line, right? So what we're saying here is that the test, the system running in hardware is behaving much more predictably. And I should tell you that's partly because we're only using the on-chip memory. So we're not using DRAM as probably the Linux implementation is using. So we get much more predictable performance. It's not only because of the memory, but it's also because of the multiprocessing happening on the CPU, right? And it's to do with the stochasticity of the PCI bus and the interrupting the CPU in order to get the DNS server, once the packet has made it through the Linux's network stack, to get the DNS server to process that, right? So you have these different kind of kinks in a chain that all need to pull together, whereas in our system we get much more predictable performance. So the takeaway message here isn't that FPGAs are awesome. We are comparing two very different things, but this is showing us the kind of performance that we can get if we can kind of structure the server to prioritize serving certain requests from one-chip memory in this case, and also removing the distraction of as I mentioned, having a multi-core CPU and interrupting the CPU and contention in the PCI bus. Right? So this is a much simpler layout, and we gain because of that. So this talks about latency for DNS. We got similar advantages in the measured latency for memcached. So memcached you can think about as maybe a more flexible form of DNS in the sense that you can carry out lookups, key lookups, but you can also update and delete keys. We also measure throughput, and there the system performed very well, as you can see. So here the results are measured in thousands of operations per second, and it is against Linux. I should also remind that we're not exactly comparing like with like here, but we are comparing a C# implementation of memcached, the transient FPGA, with the standard memcached server running in Linux on a CPU. And the appeal here is that, well, you're getting certain performance improvements that you kind of would expect to get, but you are getting them by writing the code in C#, which is not the kind of traditional way of coding for FPGAs. Okay, so so far I've talked about development. What about debugging? So in the time I have, I'd like to talk a bit more about how we try to improve this. So we came up with kind of a notion called program-hosted directability, and this builds on a lot of prior work on debugging. So when you're running in an FPGA, unlike when you're running on a CPU, you don't have an operating system to support you, and you don't have CPU support for debugging either. Modern CPUs provide registers for supporting you for that. So it's not that when you run on an FPGA, you're running bare metal, but you are the metal. So not any features that have not been included in the program at compile time are not going to be provided by the runtime on the FPGA. So what we tried to do is come up with a systematized way of having programs include their own debugging features. So having features that you can commit to at compile time that will be available for you to interfere, to influence, to read the memory of the program at runtime. So this works by having the program being extended, right? So it's I think this picture kind of conveys what's happening there. That we want to preserve as much as possible the original program behavior, but we are embedding a controller in the program that can receive instructions from what we call a director. And these instructions can be, for example, tell me what's in that memory location, or it can be set that memory location. But we also want to be able to support the high-level debugging instructions that we've come to be accustomed with in software. So we also allow kind of changing some of the code in a very controlled way that's running in different parts of the program. Let me give you an example. So say we have the program I show you there on the left. So we have a call to function G, then we're calling function F with parameters X and Y, assigning the result to V, and then we're incrementing that. Now imagine that we want to run a command, a directing command or a debugging command, trace, where we want to trace the values that are assigned to a certain variable, we trace to a certain variable, and we are specifying the maximum trace size, right? Because this is hardware, we can't make any undue assumptions about resources, right? So this all needs to be statically agreed upon at compile time. So one way to do it would be to snip in a piece of code that would behave as follows. So for one thing, we would need to have allocated additional pieces of memory to keep track of the current index that the trace has arrived at. And also another indicator of whether whether we stopped because the memory overflowed. So let me run through this code quickly. So we have an if statement that basically says, if I can continue tracing, if I still have memory left, if I still have space left in the array, then I'm going to do so, right? So we see the obvious behavior here, that we're going to assign a value to the array, we're going to increment the index and continue. Otherwise, I'm going to set a flag that I stopped because I ran out of space, and I'm going to break. And most of this is pretty uncontroversial semantically, except for continue and break, right? So those are instructions to the controller that sets the program in a different mode. So this is kind of the intuition that underlies this. We have a certain control flow structure. We intersperse it with locations which give us vantage points to the program. We have the program memory being extended with location code, so that each of those red dots there, when the control reaches them, they execute a particular piece of code that's put there at runtime, and the controller can see everything. So we have this kind of shared existence. The controller is not only sees its own memory, but also the programs. And we can then, at runtime, activate these locations and have them behave in different ways. So in this case, we are tracing with variable v, and by having the director specify that to the controller, we're updating the location code memory that is independent from the program memory. So this involves writing in a very simple programming language that does not support in loops, for example, and it only supports moving things around in memory and carrying out simple arithmetic. But it is to that language that high-level directing commands, shown on the left, are translated to. Right? So the idea is that you, as a user, you're presented with an interface, that high-level interface, which is very, for those of you who have used GDB or similar debuggers, very, very familiar. Then at compile time, the resources are made available to be able to run the translated code from those commands at runtime. Moreover, you can reconfigure that. Now, for those of you who have used FPGAs, you know you've come across logic analyzers, and there's a very similar deal there, right? So at compile time, you might want to you commit to being able to monitor certain signals, for example, and that's what we're doing here, except that it's generalizing it far more from simply tracing, but also to being able to reconfigure what you were debugging at compile time, at runtime, and supporting more commands. So the really cool thing about this is that whereas previously with the workflow I showed you, the hardware target and the FPGA target and the CPU target were run and debugged separately using kind of separate techniques. This provides us with a uniform interface because both manifestations of the code, be they running in an FPGA or in a CPU, both expose the same controller interface. So the director can instruct and exchange with them irrespective of whether it's running on an FPGA or a CPU. So we've measured, okay, how much does this cost us, this generality? And we've measured this against a logic analyzer. So for those of you who are familiar with the Window, this is basically allows you to trace the behavior of certain variables of certain signals in an FPGA. So we ran some tests where we, in addition to having support as kind of simulating the behavior of the analyzer by a trace, we also wanted to carry out certain counts. For example, to count the number of times a variable was read, or the number of times a function was called. And keep in mind that in an FPGA you don't have a call stack, right? It's a circuit. So this technique allows us to preserve the kind of the reference runtime model that we have of how the program is behaving. For example, by function calls being put upon the stack. And so the costs we get are measured in terms of logic and memory, and it is rather expensive. But we haven't yet measured how much this cost gets amortized as we add more features, right? Because what we're doing here essentially is adding another specialized microcontroller that interprets the translated language that I showed you, this simple debugging language for reading and writing to memory. So sure, adding such a generic facility will cost you in terms of circuitry, but if you can share it amongst different locations, then it's likely to be amortized over usage. And the cool thing about this is, so we also compared feature by feature what this approach can support relative to other approaches. And it does allow us, despite running the artifacts on FPGAs, to regain many of the features, the debugging features that we're familiar with from writing and running software on CPUs. So I can go into detail more question time. Okay, so to wrap up, the goal of this is to try to use HLS for developing network programs, as distinct from taking a straight up hardware description language approach or a cell approach. We gain existing tooling. For example, we don't have to rewrite the C# compiler to use that, or debuggers to do that. And we have to we came up with kind of techniques and libraries to support this and runtime environment, to also make it as easy as possible to run this in software, right? So you specify your network logic, but you also need the environment to then wire it up and connect it with some form of network card, with virtual or real. That is the counterpart of the hardware environment in which you can run it in. And we hope that this will help experienced hardware engineers, and maybe novices as well, who don't have to think as much about the hardware environment in which this is running, but can hit the ground running, as it were, and write C# programs that work in both hardware and software. Great, so that's all I have. I'm happy to take questions.
Thank you very much.
Is this available now, your work, or is it just...
Point to the dark, yeah.
It is.
So the URLs I gave, they're live. They contain code, and the code has been run by several people. So it's not just code that's running on one laptop in the world and that requires very specific things. Not everything is. Ultimately we want to make everything open. We're still polishing some things, but I think the Kiwi compiler has been made open source this month, or will soon be. But the packs, the software runtime environment.
It's open source on GitHub, is it?
It's open source on GitHub. That's right. Yeah. So I'd be happy to give you the URLs.
Yeah. You mentioned that you could get FPGAs on Amazon and on Azure. Is that only for VPNs, or just a general purpose user? It's just if you've actually rented VPN.
So I'm not sure about Azure. I do know that Amazon is currently trialing a service they call F1 that allows you to have FPGAs available to your EC2 instances, I believe. But I think that's still under trial. So I think people can sign up, and then depending on.
But it was on EC2, presumably that means it could be AWS. Yeah?
Oh yeah. But yeah, I think it's still not a fully open development. But.
Questions, please. Comparing the domain-specific languages to the generic HSL type languages, is the strength of the DSL that actually it's closer to the hardware and more low level, and that's where it's more suitable? Or is it actually that because of its niche nature it can be more abstract and the compiler can do more? Which way round?
So the DSL favors, by virtue of design, favors a domain, not necessarily hardware. If the domain happens to be hardware, then a DSL by design capture abstractions or primitives that kind of are relevant to the thinking about the programming at hand. But the DSL could be about financial instruments, for example, or in this case about network processors. So the programming, the mindset that's used to write code in those DSLs is usually very focused to the kinds of tasks one would need to carry out in those domains, network processing, for example. But because of this focus, then writing a higher performance backend for a compiler for these DSLs can be a more straightforward affair, because you don't need to support any form of code that the programmer might write, but rather you can focus on any form of code that they can write in this DSL that often is constraining enough to help them not make mistakes, as well as help them be productive. That's another advantage of DSL.
Okay. What tools have you used to implement your processing from original language to the intermediate presentation?
So mostly, I think in this project, the hardware side is written in Verilog. The tools are written in C# and F#, and there is, as ever, kind of a healthy sprinkling of Bash and Python for testing.
No, I mean language-wise, when from the higher level language post-processing to the lower level language, to closer to different presentations.
So
Have you used any transformation tools, or how you did it?
so the compiler is written in F#. So that's F# is Microsoft's functional programming language that's based on standard ML.
Question, please?
So the diagram you showed at the beginning shows what we think of as an FPGA, so the two-dimensional grid. Are there different topologies of FPGA, both physical and logical? And do these topologies present issues from the difficulty of programming them?
So from at a distance, not really. They're all organized in a grid-like fashion, and there are logic blocks and memory blocks. There is different sorts. So I did abstract over the interconnect, the wiring. So some wiring is intended to interconnect adjacent blocks. Other wiring is intended to connect more long-distance blocks. Other wiring is intended to connect every block. For example, for clocks, right? You want to synchronize kind of large parts of the FPGA. So this needs to reach everywhere at the same time. It's a signal with a high fan-out. So physically, there is provision made for that. There is difference between different FPGA devices and whether, for example, they have a higher ratio of so-called specialized hardened blocks. For example, you might have DSP. You usually have DSP units, digital signal processing units, inside CLBs distributed around the FPGA. If the product was intended to be used for operations that can benefit from this facility. But I think by and large, it's the same kind of grid, and having specialized instances distributed around this grid, and having wiring that's adequate to have to have everything interconnected in a reasonable way.
Is there an advantage in using Microsoft-style languages like C# over C? Some of the people I work with use C, not
Great.
C#.
Personally, I'm fine for any language. I think, and C has been also a great language for programming all sorts of devices, right? Various kinds of microprocessors and also kind of more heterogeneous devices. So I think one could argue for using any language. I think there can be advantage to picking any language. I think one of the advantages of C#, and C certainly has other advantages, but one of the advantages that C# has is that it's a bit more conservative in its typing regime, and it's less permissive of carrying out kind of liberal casts. Although this can be done, should the need arise, but by default it's less permissive of that. Another advantage is abstraction, right? It's useful sometimes to think in an object-oriented way and to have facilities that the standard library provides. But on the other hand, I appreciate that some tasks are better written in C, where you can rely on a more frugal runtime, for example, and you might want to control your use of memory much more. There's different tools for different jobs.
I mean, presumably if you're generating CLR code, then you can use any .NET language.
Yeah, and one of the authors the primary author of Kiwi, David Greaves, I believe is currently working on a C++.
VC++.
So using, there's a project called GCC to SIL.
Alright.
So taking code that was originally that went through GCC
Right.
and produced SIL and then compiling it using Kiwi to Verilog. But as you say, since the code is in bytecode, it could have been written in Visual Basic, F#. Yeah.
I was just wondering, the title is, about how you use this for network programs. Was that because this technique particularly lends itself to network practices, or is it just the domain that you were working in?
Yeah, no, great question. No, I think it's more the latter. It's more the domain that I happen to be working in. Other than the runtime support for running this in software and hardware, being more biased towards networking. Other than that, I think there's little that inclines it towards, that kind of necessarily inclines it towards networking, right? Because as ever, the code that you compile could be some form of network-related code. This could be a packet processor, or on the software side, we even have a user-land implementation of TCP. But it could equally be any other algorithm that's processing data that's being presented to it via some bus in some fashion.
Shortly speaking, can you take, let's say, some particular Cisco switch, describe it formally with your language, and then implement it in FPGA, exactly the same functionality?
In principle, yes. In practice, that would be very difficult. Because one would need to obtain a very clear description of a commercial product in order to build a formal model of, right? So if there were to...
The majority of the functionality is just defined in the protocols, they do. Plus the network location tables, blah, 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 which is sort of already formalized in many...
It's standardized, right?
Right.
They use standard.
Nobody yet attempted it.
So I guess my answer was more that you might not necessarily end up with an exact model of the Cisco switch, but certainly a switch or a router, yes. But if it has to be specifically a certain vendor's switch, that might be a bit more tricky, because there might be...
No, just like a concept that it is
yes,
doable,
yeah,
right?
concept.
And if it is done performance-wise, would it be comparable, faster, slower?
Yeah, so there it depends, because if the switch or if the network hardware is using an ASIC, so a dedicated circuit, rather than an FPGA, which is a reconfigurable circuit, then the switch would have a performance advantage, because an FPGA, because of its reconfigurability, adds overheads. So there would be latency that is incurred because of using the reconfigurable logic.
Right. So you mean that actually the switch will be performing the same way, but will be slower than original hardware on the implemented switch. But it will be still suitable, let's say, for modeling and kind of finding new ways to create new switches and routers.
Well, that's right.
Before they are implemented in different hardware.
Yes, and that's a big advantage of using something like FPGAs, because to produce a dedicated circuit can take a lot of time, and certainly takes a lot of money to generate the masks to create this circuit. But an FPGA is comparably much cheaper, and also the development cycle is much shorter.
So, but if we talk about networking, if we talk about gigabit, let's say, links, that you say that FPGA will be probably not the best
No, it
performance?
can certainly do gigabits. No,
Can do
FPGAs,
Okay, there's certain limits of the, how much processing can be done on each packet or whatever, okay. And then it is still possible to use it for other type of applications when you can imagine a scenario that you buy something from Amazon and with the tools available, can somebody do their own, like customized hardware, right, from FPGAs at home?
That's right. So we're talking earlier, one can also buy kind of hobby boards containing FPGAs with licensing and tools to be able to program these at home. But going back to bandwidth, so the measurement we have on the switch so the measurements I showed you were made in May, and there we didn't saturate 40 gigabits, but so we're at 32, whereas we should be closer to 36. But we've made improvements since, so you should be getting much better performance. Yeah.
So, but you're not working on wireless, for example. Was there any versions of FPGAs related to wireless, which would be absolutely new?
There could be, right? Because an FPGA is ultimately just a computing device that is going to be interfaced with using signals, and these signals, in our case, they connect to transceivers on a physical to a physical medium, but it's equally feasible in principle to have, even in practice, to have the medium not be a physical one, right? To be wireless.
Because the modern implementation of Wi-Fi are more kind of programmable shape of the signals other than just hardware implementation and various techniques like that. More questions, please?
How large can be program written this way?
So large in terms of
Lines of code, something.
I'm not sure. So I had a similar question recently, where they asked, what's the limit of programming on an FPGA? So the limit in practice is the exhaustion of all the logic and memory resource, right? So you're building a circuit, and each line of code is being translated to subparts of these circuits. And you might be able to optimize for space by having different lines of code but that do very similar things, become the same circuit, parameterized with some signal that indicates behave this way now or behave that way later. I don't have a very good intuition about what number of lines of code of in our case C# would exhaust that. We haven't. I'm not aware. I think in a couple of cases we did exhaust it, but it was because we were generating some very very large Verilog files, and these were. So I'm trying to distinguish in my mind accident and kind of reason, right? And I think that we haven't successfully got a kind of a watermark on that. So I don't know. So just as a thought experiment, what might be a program that could really pull that, right? That could really test that. So because compilers are usually really good. They have to be good at optimizing code, right? So one of part of the compiler is going to be dedicated to trying to produce code that is less wasteful and that is smaller. So maybe one could try to get a benchmark example of that and run it through this through Kiwi, for example, if such a benchmark exists for C#.
Just expected some estimate because, if you know capacity of FPGA, average which is available today, and some average coefficient of translation from C# source code to these primitives. Well, it could be kind of estimated.
It could be very good topic for next PhD. I think we can conclude on that and continue discussions with food and wine. Thank you very much. Who received an invitation to this talk not from the Advanced Programming Specialist group? Okay, just for me to know how this works. Thank you very much. Please proceed.